So this is our title, and this is what we will be talking about, Introduction to the Challenge of Creating Quantum Mystery in FTQC's Chemical Application Research. Let me quickly introduce myself. I'm now at a consulting firm, but I haven't always been involved in consulting. I have been in this quantum computing for about 10 years ago. I started out as a researcher, and then I went to work for a trading firm. I was involved in technological development and business side. And then now my passion is in trying to commercialize technology. So you can see this slide, the same slide you saw this morning, but Deloitte goes from consulting of the business, but all the way to the research as well. So I want to introduce what we do on the research side. So Mr. Sugisaki, he's Professor Sugisaki, actually. He is a researcher. He was in the academia for a long time, and he joined Deloitte. But he's actually still continues to do research and publishes papers. Now, in terms of the ecosystem in the middle, in terms of quantum community, I think it's important that we build this ecosystem. So we're also challenging on building the ecosystem. So here, this is the technology research that we do. There's a company called Q-Era, which is a company with this great momentum. So we have a strategic alliance with Q-Era. What we're trying to do with Q-Era is, first of all, gain understanding and awareness of quantum computing by everyone so that you can take leadership in ultra advanced initiatives. And so for that reason, we're building use cases, researches, we support startups, and we help talent development. And on the right-hand side, you can see Professor Sugisaki. So in terms of quantum computing, this is it. He's the author of this famous textbook that everyone reads. And below you will see what he has done in terms of POC. So with Q-Era, he has done manufacturing and medical image analysis with Q-Era. And in the middle, this is his POC with on a drug discovery with the pharma. This is molecular simulation of protein using FTQC. And on the right-hand side, you will see quantum algorithm compression with a chemical company. So why are we or him doing this? So in terms of building an ecosystem, you will see that we are working together with global key players. We're hosting events together. In our Marunouchi office, we have an event space, and we host these events. So if you're interested in what's happening in the world, especially on the most recent trend, please participate, join us in these activities. Now, this is about what we do in terms of consulting business. It's only been about 18 months since I joined a consulting firm. These are the people. I'm beginning to realize that there are a lot of people who are interested in doing quantum, but they're not sure where to start with, and I'm giving consulting service to them. So I think one of the key questions here is, who are the players in quantum? What is the specification? What strategy is needed? So, these are some of these, consulting services that we provide. Now, I want to switch gears and talk about our initiatives in FTQC era. So you knew FTQC. Perhaps some of you may not be so familiar with FTQC, but so we had NISC, which was without FTQC, and we thought that this could be commercialized. But now beginning to see early FTQC just from about last year or so. So if FTQC is realized and if we can see reductions in error, then what would happen? The definition of FTQ or error tolerance would change or error correction would change. The ultimate error correction or fault tolerant QC, it has 0 error rate and coherence is limited, infinite. What happens then? If the coherence time is infinite, we can run algorithm infinitely. Right now, because we have noise, we're not able to do this infinitely, but you can do this algorithm. So even in our FTQC, you can do a risk of 1,000 times. So what happens if one person runs an algorithm that is 1,000 times longer? Then people who can access quantum computing will be 1 out of 1,000. But we do, in that era, we will not have a mass production of quantum computing, which would meet those demand. Right now, the development of quantum computing is very limited. It's very difficult to mass scale this. Right now, the calibration is done manually, so you can't really do scaling right now. So what can we do instead? You will need to, for example, make algorithm more efficient. And the second point is that in this era, FTQC, the algorithm that we need to work on is different from NISC age. So what would be the algorithm that would accommodate this? And the third point is that against FTQC, depending on the hardware, there's a lot of different affinity, and it's very difficult to discern what would be useful. Right until you need to look at the number of qubits or fidelity, but now you have to say this is neural atom, so you have to be flexible, or this is QFPTC, so you have to discern what's different. So if you want to be ahead in terms of commercialization, you have to be able to discern the technologies. So these are some of the issues that I think are out there, but I don't think this is all clearly defined yet. So I'm sure we will continue to see increasing number of POCs and issues that will be raised. So I have tried to plot this, what will happen in the FTQC era. So if machine access becomes difficult, then we will not be able to use the machine anymore. So we need to reduce or compress algorithm, and we will need to have companies, introduce hardware for that. And if its algorithm becomes dedicated to the machine, then FTQC, it may take time until development of FTQC. With regards to hardware, you need to work with hardware vendors in order to be able to work with the cutting edge hardware. So these are the initiatives that we have undertaken in order in light of this situation. So to the left, you can see hardware from Classic. This is using a material development of Mitsubishi Chemical to see how they can compress algorithm. So you can see the increasing number of qubits horizontally, and vertically you can see the depth of quantum circuit. But the depth is 40,000. And so this is an enormous amount of number. So by using Classic's tool, you will be able to reduce this by 97% without sacrificing accuracy. So unless you're able to do this, you will not be able to work on algorithm anymore. And on the right-hand side, you see a POC in drug discovery. This is in partnership with Chugai Pharma. In the age of FTQC, what application will be commercialized or become practical use? You look at different papers, but it's very difficult to find the right information. So it's not written straightforward. So what's necessary is that You basically need to just implement for yourself what you want to do and then discern it yourself. So from here, I will hand it over to Professor Sugisaki to discuss about FTQC and chemical calculation. So my name is Sugisaki, and I will talk about applying FTQC into quantum chemistry. So let me quickly introduce myself. Up until March this year, I was at Keio University, and I was associate professor at Sustainable Quantum AI Center and Quantum Computing Center at Keio University. So, in 2011, I started quantum computing and quantum chemistry calculation. In 2014, there was a VQ algorithm that was published, and that's how quantum chemistry became very big. So I started before that. So even during that time, there was hardly any group that was studying quantum chemistry computing. There wasn't any textbook. There wasn't even an English textbook or review on it, hardly around. And then suddenly there was VQ algorithm, and they wanted to increase people who would be doing this area, and they needed, if you want to increase number of people, you need to have a text. And in order to increase the number of researchers in quantum chemistry calculation, I decided I need to write a book, a textbook. So that's how I started writing this book. So why is quantum chemistry and quantum computing good partnership or good counterparty? Well, it's molecule that we deal with. A molecule is made of atom, and atom is made of nucleus and electron. So the property of atom is basically determined by non-molecules. In other words, atom, electron, and electron is basically quantum dynamic mechanics, so it's mechanical. So that is why we have quantum mechanics. And if you can utilize accurately solve the Schrödinger equation, then you will be able to accurately predict the molecule properties as well. So you will be able to do screening beforehand before synthesizing the molecules. So this is the quantum chemical calculation. And as you can see here, so you will need to input the molecules into the coordinates, and then you have that computer calculate this, and you'll be able to determine the molecular energy or wave function. And there's a 50 years of history in terms of quantum chemistry calculation. They already have a golden standard for this, but there is an issue. Even though there is a gold standard, if the molecule size becomes larger, there will be increased amount of calculation that needs to do. So, you will not be able to calculate this quantitatively nor qualitative. So, you can use a Schrödinger equation, but if you think various realistic approximations, calculations often reproduce experiments semi-quantitatively. And in terms of molecule, you input public inputs information. So it's, but if you want to, industrial application, you want a certain property. And in order to display this property, you need to understand what the molecule is. And that's very difficult to understand. So if you think about this in consideration, what is expected of the quantum computer? You will need to able to calculate a shorter time more efficiently. The larger molecules need to be done so. So that's why you have this mechanical studies on this. So I'm not able to write anything. So I'm only showing you part of what we have done. So what I want you to look at is you have the quantum annealing and gate type quantum computers. So you have NISQ and FTQC. In all of these domains, the researches have been done, and we have been able to deliver results. And I want to just highlight a couple of them. So you have application to chemistry. So you want to do an experiment. And in chemical calculation, you will need to basically calculate all energy. But in experiment, it's mostly energy differences. You have to look at not the all energy, but you have to look at the different energy differences. So if you're using quantum computing to calculate energy differences, then it would be very useful. And you can actually do this. So quantum phase estimation is really famous for this, but this is looking at time evolution as well. So I did a slight revision to this. So you will need to do quantum phase difference estimation, not only the direct calculation of energy differences in a single calculation, but also simplifies the control time evaluation calculation as well. So there's an advantage of making this implementation easier. So we're trying to link the fragmented molecular orbit method for quantum chemical calculations of the large molecules. So let's say there's protein. We will combine this with a fragment molecule orbital method, FMO, with VQE UCC SD method to obtain, for example, water elementary bond clusters. So this is looking at size consistency on the right-hand side with calculating using QPE. And what's important here is, if small molecules, you can be very successful with the calculations. But if you use FMO, you will be able to do this calculation. If you separate calculately, even if you calculate the energy differently, you have to do. If you use quantum computer, there's a plotter decomposition, charter decomposition. If you actually implement it, even though it's not interacting, the energy will not match. And what I have shown you here is BQE and FMO. I think I've been able to demonstrate that this does happen in both of the cases. What it's demonstrating is that even if you're successful in small molecule calculations, it doesn't work when the molecule is large. So if you have true real FTQC, if you want to do a meaningful calculation, what do you need to do? You will do large molecule calculation, and you need to identify what issues could arise. So what do you need to do a large molecule simulation? You need to do fast accelerated simulation. You can use GPU. So maybe if you do 29-bit, if you use GPU, you can accelerate by 40 times. But if you can even accelerate furthermore, how do you do that? Normally, if you do a normal quantum circuit simulation, basically you would encircle it like this, and you would start from the beginning. But you can do step by step, and you will gradually increase the auxiliary qubit step by step. So on the left-hand side, you see naive implementation. It takes nearly 2 weeks to calculate without GPU. But if you actually increase auxiliary qubits step by step, it's less than half a day. And from here, you can do increase GPU. If you use GPU utilization, you'll be able to actually increase it by like 50 times more. So in order to do some debugging, you will need to do this. So you need to improve algorithm in order to do FTQC, or you can do a combination of the existing algorithm, or maybe you will need to combine different calculations, and you'll be able to do calculations on a practical basis. Thank you very much. As I listen to him, it's so great to have Professor Sugisaki, someone like him, join Deloitte. So from here on, I would like to talk about, Deloitte, how, we want to challenge on changing the society by carrying out researches in cutting edge. So if you're interested in joining to this research. And of course, if you want to join Deloitte, we invite engineers, researchers, and consultants. We'd be happy to speak with you. And finally, I want to talk about what needs to be done in order to put quantum computers into practical use. This is more of a consultant talk. But so when would quantum computing be commercialized and what is needed? Well, it depends on the evolution of the hardware. So it's hard to say when. Maybe people would have a different answer with regards to when, but I think there'll be a large impact between 2030 and 2040. So up until then, why do we need to start now? Or what do we need to start now? Well, in order to be able to use quantum computing, there's many things you can do. You need to develop market. You need to organize the market. You need to build talents, build the ecosystem. So you have to do this before commercialization or practical use because you would be behind. So we need to start thinking about that. So quantum is still in early stage, infancy. There's a lot of issues accumulating. But again, this also gives you an opportunity to succeed as well. So I hope that you will join this challenge in creating industries and use cases and businesses through quantum. Thank you very much.